Hello class, and welcome to our presentation on the Solis Sentinel. It's a glider-style solar-powered UAV designed for long-endurance missions. Combining sustainable energy with aerospace and military-grade capabilities, this unmanned aircraft is built for tactical surveillance, remote operations, and environmental monitoring, all with minimal environmental impact. Let's take a deeper look. Let's start with the key innovations that make our UAV flight-ready. When it comes to traditional solar panels, they rely on heavy, rigid materials like glass and aluminum to withstand years of weather exposure. While this is ideal for rooftops and other stationary setups, it poses a serious limitation for aircraft applications. In contrast, our UAV uses ultra-lightweight, flexible solar panels specifically designed for aerospace applications. By sacrificing some long-term durability, we gain significant weight savings and efficiency, which is critical for sustained high-altitude missions. To achieve long-duration flight, the Solis Sentinel integrates advanced aerospace materials and technologies specifically designed to reduce structural weight. Instead of conventional, heavier materials used in standard solar panels, our design utilizes thin amorphous silicon solar cells mounted on ultra-lightweight substrate. These flexible cells drastically reduce weight while still maintaining sufficient energy output for sustained flight. We've replaced rigid panel framing with foam core structures and cellophane film layers, significantly cutting down mass without compromising aerodynamic stability. These material substitutions enable the airframe to be lighter, more adaptable to high-altitude conditions, and capable of housing a broader surface area for solar collection. This transition results in a massive reduction in solar cell weight, from approximately 2 to 4 pounds per square foot in traditional systems, to as little as 0.03 to 0.2 pounds per square foot in our UAV. These weight savings are critical, as it allows the aircraft to remain airborne for weeks or even months, powered entirely by the sun. One of the biggest challenges for solar-powered UAVs is maintaining power during the nighttime or poor weather when solar input is minimal. To overcome this, the Solis Sentinel uses a hybrid storage system that charges during daylight hours and supplies power when sunlight isn't available. The primary component is a set of high-capacity lithium-ion batteries, known for reliability and efficiency. We also account for emerging technologies like solid-state batteries, which offer higher energy density, faster charging, and improved safety. In the future, lithium-sulfur batteries could further enhance performance with up to 5 times the energy density of current lithium-ion cells, extending the flight time while further reducing weight. One real-world example of solar-powered flight is the Skydweller, an uncrewed aerial system developed by Skydweller Aero. Powered by solar panels and onboard batteries, it can stay airborne for over 90 days without landing. It operates at altitudes up to 45,000 feet and carries up to 800 pounds of surveillance or communications equipment. With a 236-foot wingspan, it's a clear example of how solar technology is already enabling long-endurance, zero-emission flight. Our aircraft being designed for high-endurance missions makes it ideal across both civilian and military sectors. Its ability to fly at extreme altitudes for long periods makes it perfect for environmental monitoring, wildlife tracking, and climate observation. On the defense side, it can support persistent surveillance, secure communications, and with the right payload, precision missile strikes in high-risk or remote areas. This combination of endurance, versatility, and low detectability makes it a valuable asset for modern aerial operations. The Solar Sentinel represents a major step forward in the future of aviation. Its ability to perform long-endurance missions at high altitudes opens the door to new capabilities in both environmental and military operations, from surveillance and research to communications and disaster response. As solar and battery technologies continue to advance, aircraft like this will play a growing role in sustainable aviation. With its innovative design, the Solar Sentinel has the potential to redefine how we explore, observe, and protect the world around us.
Hi everyone, I'm Alfredo, and for our team's solar-powered UAV project, also known as the Solar Sentinel, my main role was creating the CAD design, which you'll see in the time-lapse playing alongside my explanation. Let me walk you through the design process and the key features we focused on for our UAV. Our goal was to create a lightweight, efficient, and sustainable UAV that could stay airborne for long durations using solar energy. After a few brainstorming sessions with the team, we agreed on a fixed wing design with a high aspect ratio. That means long, narrow wings, which is ideal for maximizing lift and minimizing drag. That feature is especially important in solar UAVs where efficiency is everything. Due to our available resources, I used Tinkercad to build this model. While Tinkercad is more basic compared to professional CAD software like Fusion 360 or SolidWorks, I still managed to create a decent model by breaking the UAV into modular components. The time-lapse you're watching compresses several hours of modeling work into just a few minutes. It shows the iterative nature of the process. There were times I completely scrapped and restarted the design, or adjusted the wing angle for better realism. I had to really think about the proportions and scale. Make sure everything would make sense for a UAV of this size. I also added a few items that I borrowed from other existing Tinkercad models. This part of the project really showed how the design and engineering come together. While this CAD model is purely visual, I tried my best to base every choice on real-world engineering principles. Obviously, some details like material weight, electronics, and internal structure aren't shown in full detail, but I still kept those ideas in mind throughout the process. There were several design considerations that we did agree on as a team that I implemented as best as I could. Some of the most important ones I included were wingspan and solar panel integration. We wanted to give our UAV as much surface area as possible to mount solar cells. That's why the wings are long, thin, and flat on top. The ideal configuration for catching sunlight throughout the day. I designed the top of the wings to act almost like a solar panel bed. Another one was material selection and structure. While I couldn't model materials in Tinkercad directly, we imagined using advanced lightweight composites like carbon fiber or reinforced polymers. These would offer strength while keeping the UAV light, which is critical for solar-powered flight. Another one we considered was aerodynamics. It was designed to be sleek and narrow to reduce drag. I spent a good amount of time refining its shape, starting with a more chunky design at first, then eventually making it smaller to create better airflow, as you could also see later on in the time-lapse. The tail assembly was kept minimal but functional for directional stability. Another feature I want to mention is the rear propeller setup. We went with a pusher configuration, meaning the propeller is at the back. To keep the airflow clean over the wings and improve efficiency, it's a small detail, but it has a real effect on performance. And as you can probably tell, the overall shape of the plane became thinner and more streamlined over time. That wasn't just for the looks, it was an intentional design to support our goals of efficiency and endurance. One of the real-world inspirations we looked at during our project was the Skydweller Aero, a solar-powered aircraft that's currently being developed for ultra-long endurance flight. What's incredible about the Skydweller Aero is that it's designed to fly for months at a time without landing, completely powered by the sun. It was originally based on a record-breaking plane called the Solar Impulse 2, which flew around the world using only solar energy. Skydweller takes the concept even further by adding full autonomy, which means no pilot is needed. It's being developed for missions like surveillance, communications relay, and environmental monitoring. Exactly the kinds of things we imagine for our UAV. Seeing what companies like Skydweller are doing really showed us that our concept isn't just a school project. It's actually aligned with real cutting edge aerospace innovation. It made our design feel more meaningful and also gave us ideas for future improvements like autonomous navigation systems or energy storage solutions. In conclusion, the CAD model helped our team visualize and refine our concept. It serves as a foundation for future steps like simulation, prototyping, or even a real scale model. By combining renewable energy with UAV technology, we believe this design could be a step toward more sustainable aerospace solutions. Thank you.
Hey everyone, I'm Chris, and I'll be walking you through the second half of our solar powered UAV design time lapse. At this stage of the project, the major components were already in place, so the focus shifted towards refining the design, exploring new ideas, and making the model feel more complete and functional. We began with some detailed adjustments to the wings. This meant revisiting the wing shape, fine tuning the angle and surface area, and improving symmetry. While the changes might seem small, they were essential, especially when considering the integration of solar panels. By making the wings flatter on top and more uniform overall, we gave ourselves a much better surface to work with for more energy collection. These kinds of subtle edits really add up in the bigger picture for efficiency and flight stability. After the wings were in good place, we shifted focus to a completely new element, designing a rocket model to attach under the UAV. This was one of the most exciting additions to the build. The idea behind it was to give the UAV modular capabilities, allowing it to carry and deploy specialized payloads. Think of it as a flying platform that could launch environmental sensors, small research probes, or even emergency communication devices in remote areas. Or we could just use it to blow up Elon Musk's house or something. But we started out by sketching out the basic rocket body using simple geometric shapes, then gradually layered in details to give it a more realistic look. Things like fins, a tapered nose, and a cylindrical engine section. Even though we were using Tinkercad, which is a more limited than other CAD softwares, we tried to make the model as true to form as possible. It had to look compact enough to fit under the fuselage, but detailed enough to fit like a legit functional component. We imagined scenarios where this rocket could be remotely released mid flight or during a stationary hover, delivering scientific tools to hard to reach locations, maybe even on a future version of this UAV. That kind of flexibility is what makes solar UAVs especially promising for long range missions, especially when paired with low energy payloads like this. It also got us thinking about mission planning. Where would this rocket mount be located? It would be a one time deployable piece or part of a reconfigurable pod system. Even in a visual model like this, these questions were shaped like how we placed and proportioned the attachment. So we tried to balance the visual realism with theoretical functionality, making sure the rocket didn't interfere with aerodynamics or the plane's center of gravity. This section of the build not only brought in a cool design element, but really pushed us to think the creativity about the multi-mission platforms, the kinds of systems that can adapt to different tasks, whether that's scientific exploration, remote sensing, or even a disaster relief. Once the rocket model was complete, it was time to revisit the main body of the aircraft. One of our priorities was to make the fuselage more aerodynamic. So we worked on narrowing the central structure and reshaping the nose to reduce drag. This not only helped make the UAV look more streamlined, but also reflected the kind of efficiency we're aiming for in a solar-powered platform. A sleeker body means better airflow, and a better airflow means more range and stability during flight, especially on long endurance missions. These edits required a lot of careful adjustments. It's easy to get caught up in small details. Keeping an eye on overall proportions really helped everything feel balanced and intentional. Towards the end of the time lapse, we focused on finalizing the rear section of the UAV. This included modeling the tail fins and vertical stabilizer, essentially components for maintaining directional control. We also added the rear mounted propeller, which is part of what's known as a pusher configuration. This layout helps improve the airflow over the wings and reduce turbulence around the main body. Getting the positioning and scale ready for these rear components was surprisingly tricky. We had to make sure they looked functional while still fitting with the aesthetic and engineering intent of the design. The rear end might not get as much attention as the wings or nose, but it's just as important for overall flight performance. Looking back at the second half of the build, it really highlights how important iteration and detail are in the design process. Every adjustment from the curve of the wing to the position of the propeller is a small step towards making the concept more believable and potentially real. This time lapse is more than just a speed up of our CAD work. It's a visual representation of problem solving, creativity, and teamwork. And while this model isn't flight ready just yet, it gives us a strong foundation to build from, whether in simulations, physical prototypes, or future design revisions. Thanks so much for watching. We hope our project sparks ideas and shows what's possible when you combine sustainability with aerospace design. We're excited to keep pushing forward, and we can't wait to see what comes next.
Before the clips begin, I'd like to mention a disclaimer. Please know that the following clips containing planes and drones are just used as a reference, and they are not our solar panel UAV, as you will see big aircrafts, pilots, and drones in the following clips. The Solis Sentinel is an aircraft that was made mainly for military purposes. Now to mention the major details and ability that make the Solis Sentinel a great innovation. Firstly, the solar power technology. At the heart of the Solis Sentinel is its cutting-edge solar power system. Equipped with high-efficiency photovoltaic cells, it can harness solar power energy even at high altitudes like being above the clouds, which benefits us and the military as no one will see it coming. This allows for extended flight durations without the need for refueling, ensuring continuous operations during critical missions. Secondly, another cool feature is the remote control capabilities. One of the most remarkable features of this aircraft is its ability to be controlled remotely from an office, a facility, or anywhere in general. It can even be located in different zones, such as states, countries, cities, anywhere. Utilizing secure satellite communication links, operators can manage a drone's function and navigate complex environments with precision, all from a safe and distant location. The Solis Sentinel has military applications as well, designed with versatility in mind. This drone is equipped to carry various payloads, including advanced surveillance equipment and defensive systems. Additionally, it has the capability to be armed with weapons such as bombs and guns, and the general equipment used for firearm activity, making it a formidable asset for strategic military operations. This aircraft would also only be able to be bought by our military. Eventually, maybe having contact with other countries if we have an alliance with them. But even so, it is mainly for our military. And finally, the operational advantages of the Solis Sentinel. It has the ability to fly above the clouds, as we had mentioned before already, and provides a tactical advantage by keeping it out of reach from ground-based threats, such as missiles and watchtowers, while maintaining a clear line of sight for reconnaissance and targeting, which allows us to basically fly in incognito. Because unless you're looking up and trying to see an aircraft in the sky, you won't see us. Especially if you're in an area surrounded by buildings or in a place where it always gets cloudy. Its solar-powered design also ensures minimal environmental impact and reduced operational costs. In conclusion, the advanced solar-powered drone represents a significant leap forward in military technology. By combining sustainable energy solutions with cutting-edge remote control and combat capabilities, it offers unparalleled advantages for modern defense strategies. Group 3 wraps up this presentation by saying thank you for your time and your attention.